Hi guys, let's get started today's class. All of you remember the assignment last week, and I would like to start from that assignment. This is the practice, the calculate temperature of the system after mixing the cubic of the copper and cubic of the water, you know, mix up and what's happened, how much temperature, uh, you know, was obtained after mixing these two materials. And the important keyword is mCAT. Okay, so you can calculate the temperature after the mixing by the use of this equation. Important thing is Q kappa plus Q water equal 0. That means before and after the reaction, any heat cannot go away from the system. Okay, so if you can determine the final temperature as a TF, the mCAT, I mean the Q kappa, can be calculated by this equation: 0.5 kilogram of copper, the specific heat constant. Do you remember? Specific heat C is 387, and delta T can be defined as TF minus 90 degrees C. Plus, how about Q water? 2 kilogram of water times 4146, this is the specific heat, times TF minus 20 degrees C equals 0. Then you can calculate by this equation, and TF times 193.5 plus 8372 minus this value, okay, equals 0. Then you can calculate the final temperature equal 21.58 degrees C. This is the answer. An important thing is the initial temperature of water is just 20 degrees C. After adding red hot copper cube, the temperature changed just 1.58 degrees C. That's why we use water as an heat sink. Water is very special. I mean, specific heat of water is so high. You can add a lot of heat that doesn't change its temperature much. This is very unique character of water. Then always we use water for example the cooling down of the heat materials, such as the nucleophilic reactor, or many kinds of reactors. Okay, and why the water have a very high specific heat? The answer is here. Water makes the hydrogen bond. Then, after heating the water solution, these hydrogen bonds can easily destroyed or reconstruction. Such kind of change of the hydrogen bond network can consume a lot of heat. This is the reason of the specific heat of water is so high. Okay, here I would like to show you the review of the first session. Our goal is evaluation of the chemical reaction. In order to do that, I introduce the internal energy, U, the universe of energy. And if you add heat or pressure, the internal energy can be changed. So this is the initial internal energy, Ui. This is the final of the internal energy, Uf. And the difference of the internal energy can be described by Q plus W. Q means the heat and W means the work. Work is pressure and volume, pressure delta V. This is work. But internal energy is not appropriate to describe the reactivity. Can you imagine that? Do two states with the same internal energy show the same reactivity? Large volume and low temperature one, small volume and high temperature one. All of you can understand this high temperature one should be much more reactive. It's energetic and it can go out, spread out many energy from this small volume but high temperature one. But internal energy of these two materials are completely same. So internal energy is not the perfect one to describe the reactivity. Such kind of value should be the factors of pressure and volume should be included. Internal energy is not appropriate to describe the energetic state. This is one of the important issues for us. And next video, we want to discuss about this kind of some other kind of expression of the energetic state by the use of the pressure and volume. See you next video.